formerly BESU or BE College, Shibpur, MS from Sunny Albany, USA, and PhD from Indian Statistical Institute, Kolkata, all in computer science. He was a faculty of Jadavpur University in Computer Science Engineering Department for 7 years and has been a faculty of ISI Kolkata for the last 12 years. His professional research area is classical cryptography as well as quantum computation and communication. Since 2024, Dr. Paul is also serving as the regional coordinator of the Mathematical Olympiad for West Bengal region under National Board of Higher Mathematics, NBHM, India. Dr. Paul received the prestigious Alexander von Humboldt Award from Germany and the Young Scientist Award from the National Academy of Sciences, India, along with other accolades. Till now, Dr. Paul has supervised 6 postdocs, 16 PhD theses, 24 master's theses, and close to 100 bachelor's projects. He has also authored 2 technical textbooks and around 150 refereed technical publications. So far, Dr. Paul has delivered around 200 invited technical lectures, excluding conference paper presentations, as well as more than 100 motivational speeches, including 2 TEDx talks. I would now like to request Professor Paul to start the session. Over to Sir. Sir, please start. Sir, I think you need to unmute your microphone, sir.
Okay. Yeah.
Yeah. Now you are audible, sir.
Now I am audible. Okay. So I will share my screen. So is my screen visible?
Yes, sir. Yes, sir. It's visible.
Okay. Okay, fine. So I'll just turn off my camera. Okay. So is the, can you see my screen?
Yes, sir.
Okay. Good. So let me know if you know there is an interruption or issue with it. Fine. So the title of the talk is Classical versus Quantum Machine Learning. So before I proceed, I would like to know from the audience that what do you understand by machine learning? Okay, then we can come to the classical versus quantum part. Anyone from the audience, what is machine learning?
Audiences are requested to respond to the sir's query. Sir wants to know how much do you know about machine learning, right, sir?
No, I'm sure. I'm sure they know about machine learning. They have taught courses on machine learning.
Yes,
and
yes, that's right.
They are, some of them are experts in machine learning. So I just wanted to know in brief to have the setting for all of us to have the common setting. So I just wanted to make it interactive. So just maybe in 2 lines, I'm requesting their input on what is machine learning, or how is it different from the so-called AI.
Hello, sir.
Some people, AI means machine learning, right? So I think Orpita wrote a subfield of AI related to big data. Okay, so
Hello,
does
sir.
it mean that if the data is not big, we cannot call it machine learning? Does it mean that?
Hello, sir.
Hello, yes.
Actually, machine learning is a subset of AI in which we teach machine with respect to algorithms towards some objective or subset prediction or regression. And AI is a branch of computer science in which we try to mimic the human behavior with respect to towards some goal or objective. So that's the difference I get.
Right. So basically, in artificial intelligence, as the name suggests, we try to mimic the real human intelligence. Okay. And we do not completely know how the real intelligence works, except some neurotransmitters, some centers in the brain where some processing happens, some models of memory, short-term memory, long-term memory, etc. But exactly what happens, is yet open. So that's why when people try to model the real human intelligence by artificial intelligence, there were several paradigms. So one paradigm was rule-based AI. Means we know from our traditional programming concept that we have conditional statements like if, else, etc. So they tried to formulate certain rules and feed it to the machine. That machine will check the condition, and depending on the condition, the machine will take some action. So there is a sensor, and suppose temperature from the environment is being read. So if the temperature is below this level, certain action has to be done. If the temperature is between some limit, some other action has to be done. If the temperature is above some limit, some other action has to be done. Right? So, or I'm navigating something, I'm calculating my speed, I'm calculating the distance from the obstacle, I'm calculating the direction of my motion. So depending on the magnitude and direction of my velocity, and depending on the position of the obstacle, dimension of the obstacle, I need to take certain decision. And I can make the whole thing as an if else, if else, if else sequence of conditional statements. So there it is rule-based decision making or rule-based intelligence, but there is no learning involved. Why there is no learning involved? Because if I run the same system with the same input, the system is not going to use its previous experience in order to take the appropriate action. It is going to repeat the same conditional checking, the same if-else sequencing, and choosing one action. So there is no learning involved. Every time it is looking at the data and looking at the condition afresh. So machine learning is definitely a field of AI, but the difference is that in machine learning, the concept of learning is involved. We can understand the concept of learning, with the example of a child, right? So when a child grows, child observes alphabets, a child, they listen to the pronunciation, they identify patterns. Okay, in school we teach them, okay, this is called a triangle, this is called a circle, okay, this is called green color, this is called red color. So we give the children lots and lots of data, and from the data in their brain, some model is generated. Because of that model, next time if we show them a larger triangle or a smaller triangle than what he or she has seen earlier, because a model of triangle is there, the concept of triangle is there in the brain, they can still identify. Even if the shape is similar, but the dimension is different, or maybe the angles are different. Okay, so that is where learning is involved. In other words, AI can be rule-based, AI can be decision tree-based, AI can be, mathematical equation-based. But if we are not using the previous experience in the future prediction, then we do not call it learning. So before machine learning came, AI had different flavors. We had a system of AI which we used to call expert system. Again, why expert system? Because if you want to use AI in a particular field, let's say you want to predict a disease, or let's say you want to draw some conclusion about sports. You are collecting a lot of data from a particular sports, it can be cricket or football, and you want to make some conclusion. So there, to interpret the data or to predict the correct behavior, we need domain experts who have field knowledge, who can map the numerical values of the data to the actual semantic interpretation that what is happening out there, whether the low value is good or the high value is good. It depends on the particular domain, right? So, or maybe a threshold is good, particularly in medical field, let's say the pressure or the blood sugar or the body temperature. So it's all about being in some range, and if it is outside that range, then it is abnormal. So we need domain experts who will give us meaning of the data, with the help of whom we can pre-process the data, label the data, and then perform artificial intelligence task. So that was expert systems all about, but again, without any learning. Now, when later on, when learning was added, means encoding previous experience and then using it to predict future, that was added, that component of AI is called now machine learning, right? Now, in the field of machine learning, there are multiple activities that can be performed. Is the picture visible?
Yes, sir. It's visible.
Okay. Okay, so the classical machine learning broadly can be classified into two categories. One is called supervised learning, the other one is called unsupervised learning. Okay, unsupervised learning is Michael Faraday, who used to work in a library, and our bookbinding shop. He used to work in a bookbinding shop, and whatever books the customer used to give to bind, Faraday used to read it, and then reading it, he became his knowledge increased. So that is unsupervised learning. Supervised learning means when kids go to school, the teachers tell them, okay, this is what this subject is all about. This is how you should classify. This is the difference between two terminologies, etc., etc., etc. So that is supervised, right? Now, in the supervised learning paradigm, in terms of data, we can model any learning process as the data or the features and the class. Okay. So every data is associated with some feature values and the class. For example, if we are talking about disease, let's say, so from every patient we can get the data, And the data will look like, it's a one feature, maybe the body temperature, another feature may be the blood sugar, another feature may be the blood pressure, another feature may be the bilirubin, another feature may be the urea, creatinine, potassium, sodium, so lung capacity, then the electrical activity in the brain from EEG. So, or the dimension of the liver as seen in the USG. So we can numerically represent multiple features. Okay. Now, with all these features, we can label that, okay, the patient has this disease or does not have. So that's binary classification. We can put a 1 and 0 as the label, or we can have a range of, real values, or let's say probabilities. Okay, 99% chance that the patient has this disease, or 1% chance that this patient has this disease. So it can be a real number also within a certain range. Now, given such a feature in the class, every data looks like a vector, right? Now, when we have lots and lots of such data, the machine learning model means we compress the data into a short representation. So recall that in, when we used to do physics experiments in laboratory, we used to plot temperature versus pressure curve, and probably would have taken 20 different readings, like pressure temperature pairs. But after we have these 20 different readings, we see a pattern, we see a curve, and then we add them together, the points, to get the curve. And the curve can be represented by a simple equation. So what we did from that physics laboratory experiment, we basically compressed or summarized 20 pairs of data points into an equation or a curve parameterized by maybe 1 or 2 parameters. So 20 pairs of values being compressed by 1 or 2 parameters. If the curve happens to be a straight line, specifically it is parameterized by 2 values, right? Like if y equal to mx plus c, then the value of m and c would denote the parameters of that particular straight line, but which we might have learned from lots and lots of data points. So I gave the example of a disease. Similarly, in different domain, we can learn, meaning we can compress the data in terms of a model. So we can have images, for example. In images, we can have multiple features. So we can divide the image into different blocks, and we can calculate statistics of different blocks, like what is the entropy of every block. That may be a feature. How many number of pixels are above a particular intensity, that can be another feature. What is the average intensity, that can be another feature. So there can be lots of features in an image, and then from that we can try to learn whether the image is of a particular type, whether it's a natural image or it's a portrait, or maybe if it is an image or an X-ray of a body part, we can try to predict whether we have a tumor or not. So, or it can be a bank application, let's say. From bank customer, we can have the age, the salary, the previous history of loans, number of fixed deposits, average monthly deposit, average monthly withdrawal, average income tax submitted every year. We can have all these as feature of every client represented as vectors, and then the bank can summarize these features in terms of a surface or a hyperplane in a high dimensional representation. Okay. So either way, By learning, we mean we use different algorithms to learn a model. Means we have a short representation of the data. That short representation can be a curve, can be an equation, can be something else. So for, let's say, for neural network, this short representation is nothing but the weights that connect the nodes. That means the edge weights in the neural network graph. So the weights represent the learned parameters, the compressed parameters from the huge number of data. Okay, so in supervised learning, the class labels are provided with the data. In unsupervised learning, the class labels are not provided. Okay. So under supervised learning, we can have two kinds of learning task. One is called classification, and the other is called regression. What is the difference? In classification, we have a finite number of class labels. So basically, we are predicting whether a particular entity belongs to a particular class or not. On the other hand, in regression, we are predicting a number, a numerical value. So we are not fitting the data into finite number of classes, but we are predicting a value from infinitely possible values of the data. Okay. So that's called regression. Often a regression may look like, let's say you have x's and y. So y as a function of x, you want to give a new x and you want to predict a new y, given a bunch of old x's and y's. So that's the regression, because y can be arbitrary. Okay. Now in the unsupervised setting, again, the learning tasks can be classified as clustering, association, dimension reduction, etc., etc., etc. So clustering means basically grouping of data, or try to identify which parts of the data concentrate together. For example, when we have astronomical images from NASA or any observatory, any space observatory, we see a lot of images of stars as points, as glowing points in a two-dimensional plane. And then sometimes we see that there is a grouping of stars or planets in a particular area, and there is a separation between such groups. So we can then identify whether it's a solar system like entity, whether it's a galaxy, or it's a set of stars which are sitting there together. So we can classify these groups, which are called clusters. Similarly, if we have individual, let's say in the banking scenario, we can, each individual is now represented as a vector, and since it is a vector, it will have a geometric representation. So here one cluster can mean the income groups. For example, there can be a low income group, medium income group, and large income group. Such three clusters may be possible from that particular example. So clustering means, given the input data, we don't want to classify, we don't want to predict classes, but we want to find out what are the clusters and which data point belongs to which clusters. So that is the problem for clustering. Similarly, for dimension reduction, the problem is if the data has a lot of features. Sometimes the data has a lot of features, particularly image data or multimedia data has a lot of features. Now, how to identify the most important features? Then we can get away with all the redundant features and stick to only the most important feature. This is also applicable for, let's say, patient. When we want to identify a particular disease, whether this disease has happened or not, maybe not all the features of the patient are relevant. So what are the key indicators? The doctors might be able to tell you that when you are trying to classify whether a patient has a particular disease or not with respect to that disease. Maybe certain body features or vital parameters may be more important than others. So we can choose only that particular subset. Maybe it consists of 10 feature values instead of 50 or 100. So that's dimension reduction. Now, there are automated algorithms in which if you give data with a lot of dimension, it is going to find out what are the most important features and give you reduced dimension. One such application is PCA, or principal component analysis. Okay, so that's an algorithm by which we find out the most important features. Another application of unsupervised learning is called association, or ARM, sometimes association rule mining. So let's say in the market basket scenario, a grocery store has collected data of the buying patterns of the customer. And from the bills that are stored, it can analyze that whenever a customer is buying bread, the customer is also buying butter. Whenever the customer is buying shoe, the customer is also buying socks, right? So this kind of correlation and association can be there. Some of them are obvious and some of them are not. So by studying it, they can find what are the association. That means what are the correlation? What are the items that tend to occur together more frequently in the bills? And if they can identify that from the data, an application could be that in future, when they arrange the items in the shelves, in the rows, then they can place correlated items, or the items that are bought together. You know, Amazon, when you try to buy nowadays, it gives, okay, customers who have bought this also has bought this. It gives you an option. So it comes from the same application. So it has identified patterns. It has identified which data has occurred together, and then it's trying to put them together in the shelves when we have face-to-face purchase, or when it's trying to give you the advertisement when you are having digital purchase. So that's what this association is all about. Now, here what we discussed is basically what are the machine learning tasks. That means what is the problem that machine learning focuses on? What are the problems that machine learning wants to address? So classification is a problem, regression is a problem, clustering is a problem, association is a problem, dimension reduction is a problem. Or these are the tasks. Now, in order to accomplish this task, or in order to solve this problem, in the machine learning domain, there are multiple algorithms that are discovered, which I'm sure all of you have heard. So decision tree learning algorithm, neural network learning algorithm, support vector machine learning algorithm, and blah, blah, blah. We all know they can be modeled as optimization, can have theories. These are nothing but different methods of learning. So we have that what to learn, that is given in this slide, and then we have how to learn, for which we have familiar algorithms. So that is pretty much a quick summary of what is our classical machine learning domain. So we know the algorithms. We know that if we have to train a neural network, we have to run, let's say, backpropagation algorithm, right? If we have to learn the separating hyperplane in the support vector machine algorithm, then we need to solve a quadratic optimization problem. So using the techniques of linear programming or quadratic programming. Or maybe another learning task can be modeled as a minimization problem or a maximization problem, where we are trying to minimize the error or trying to maximize the likelihood. So these are all well-known machine learning tasks, and we have well-known machine learning algorithms from the classical domain. Now, when we switch to quantum, some concepts of the classical domain is going to stay with us, and some concepts are going to be different. So in terms of computation, there are some differences in the classical and the quantum world. Let's summarize them. So in classical computing, we have bits. The analog in quantum domain is qubit. But there is a difference. Bit means binary digit, so it has two values, 0 and 1, which can physically be represented either by a high voltage versus a low voltage, or a high current versus a low current, or a capacitor which is highly charged versus a capacitor which is fully discharged. On the other hand, in the quantum domain, the corresponding concept is qubit. In qubit, we have the concept of a 0 and we have the concept of a 1, but we also have the concept of superposition. So bits represent single state at a time, like high voltage state, low voltage state, or for a memory unit, for a flip-flop, for a register, it is 1 or 0. So single state at a time. Whereas in qubit, we can have the 1 represented by, let's say, the horizontal polarization of a photon, the 0 represented by the vertical polarization of a photon. But since the polarization of a photon is a vector, like an axis, which can be aligned in any direction in the three-dimensional space, so therefore, we can have a non-horizontal and non-vertical orientation of the photon polarization vector, which can be decomposed into horizontal and vertical components. So just like a classical vector in the XY plane is a sum of its component along X and Y direction, similarly, photon with arbitrary polarization vector can be modeled as sum or superposition. So this sum is called the superposition in the quantum domain. Superposition of horizontal and vertical polarization. In the classical domain, also, we do not have entanglement. So what is an entanglement? I'm sure I was looking at the topics that have been covered today. So accordingly, I have prepared my lecture. So I've seen that this qubit and state and these concepts have been explained quite well, including entanglement and entanglement-based tasks and algorithm, etc. So therefore, I'm not repeating them in detail. I'm just recapitulating them so that we can have the classical versus quantum machine learning setting. So no entanglement. Entanglement is a phenomena by which even if two particles are many, many light years apart, two corners of the universe, they can be correlated. Means if I measure a particular particle and observe a particular value of a physical parameter, then I can predict what is the state of the other particle at the other end of the universe. It's counterintuitive because for signals to travel from one end of the universe to the other end of the universe, it is limited by the speed of light. So it is going to take a certain amount of time. For example, from Sun to Earth, light takes 8 minutes to travel. But this entanglement, state collapse, happens instantaneously. If I measure a particle on Earth and an entangled particle is there on the Sun or on the Moon, then as soon as I do the measurement and the particle on Earth collapses, immediately at the same time, simultaneously, the particle at the other end will collapse. So that is what is called entanglement. In the classical world, we do not have this entanglement. We have classical correlation. That is fine. But typically the classical correlation is limited by geography, by proximity. Two particles are correlated if they are close together, right? Maybe in the same magnetic field, maybe they are in the same electric field, maybe they are in the vicinity of each other so as to influence each other by their gravitational field. But if you move the particles away, then these classical correlations do not exist. On the other hand, quantum correlations like entanglement do exist even if the particles are taken far and far apart. Okay. Another interesting concept which lays the difference between the classical computing and the quantum computing is the cloning. The classical states can be cloned or copied, but quantum states cannot be cloned or copied unless the states are known. So if you know a quantum state, then you can create as many copies as you want by taking additional particles. But if you do not know the quantum state, you cannot make a device to create a copy. But in the classical domain, we can always copy. Okay. Whether we know or we do not know, even unknown states can be copied. In the classical domain, when we measure a physical parameter, we do not destroy the particular value. When a sensor is trying to measure temperature, it's not changing the temperature by a huge amount. Maybe by infinitesimal amount it is changing because heat is being exchanged between the body whose temperature is being measured and the thermometer or the device which is measuring the temperature. So a slight change in temperature will happen, but that is undetectable. So in other words, classical measurement apparatus do not disturb the object that is being measured. But in the quantum domain, when we make certain measurements, it actually interferes with the system and makes the system collapse to one of possible states, which we call eigenstates. For example, if we measure the polarization of a photon in a device whose eigenstates are horizontal and vertical, then after measurement, irrespective of whatever was the initial polarization, the final state is going to be either horizontal or vertical, one of the two. We call these as basis states, which are also eigenstates. So one of the two eigenstates or one of the two basis states. Okay, so that's why quantum measurement is a destructive measurement, right? I'm sure when this BB84 was discussed, or it will be discussed, then this destructive measurement will be discussed again, that Eve as an attacker sitting between Alice and Bob, if tries to guess and measure as a trial and error attack, then that can cause a disturbance because the states will collapse. Fine. So machine learning, whether it is classical or quantum, can be viewed as we have a training data, means a set of vectors. Each vector represents a particular instance, an individual or a case, or an object or an image, whatever. The training data, the set of vectors, feed into the learning algorithm. The task of the learning algorithm is to create a compressed representation of the data. That's precisely the learning model based on certain parameters. And then during the test phase, we feed test data to the learning model, where the test data do not have class levels, and the learning model predicts the class levels of the test data. So how can we know if the model is performing better? By measuring the accuracy. To measure the accuracy, we cannot have real test data, because in the real world test data, the classes will be not known. So we would not know whether the prediction is correct or wrong. So we have synthetic test data, or we can have a portion of the training data as our test data, and there we know the class level, but we'll assume that we do not know the class levels. We'll feed the test data without the class level into the learning model. The learning model will do the prediction, then we'll match that prediction with the actual class level, and we can calculate the accuracy, the percentage accuracy of the prediction. Now, if we're satisfied with that, we know it's a good model, then we can try and test with future unknown data. So this is pretty much the machine learning scenario of all classical and quantum domain. Okay. So the challenges in classical machine learning are threefold. One is the growth of data, because as we are progressing, as technology is progressing, as civilization is progressing, we are having exponential blow up of data from social media, from mobile network, from internet traffic, from online trading, from online gaming. We have tremendous growth of data every moment, right? So classical machine learning algorithms have limited processing power and limited memory to handle such growth of data. The second problem is high dimensionality, so that not only the number of data is growing, but the dimensions of the data is also growing. So you can visualize the data in the form of a matrix, where every row represents an instance. So there are as many rows as many instances, and every column can represent a feature. So there are as many features as many columns. So growth of data talks about the number of rows in this matrix, and the high dimensionality talks about the number of columns in the matrix. We cannot afford to increase both, but which is happening in the real world today. And then we have the learning cost, means in order to create this compressed model from these tons and tons of data, which we call big data, we need a lot of time, a lot of memory. So this cost is directly proportional to the memory unit consumed and the time that it's needed, because everything is built. So learning cost becomes a bottleneck in the classical machine learning scenario. So when we switch from classical to quantum computing, then we can classify it as CC, QC, QQ, and CQ based on the data generating system and the data processing device. So the first letter is the data generating system, the second letter is the data processing device. If the data generating is classical and data processing is classical, we call it CC. That's typical classical machine learning. Now quantum machine learning, the generating can be classical, processing can be quantum, or vice versa, or both can be quantum. So the first thing that comes to our mind that, okay, in the quantum domain, we can mimic our classical machine learning algorithm, but before we do that mimic, we need to know how to represent a classical data in a quantum computer. Because we know that in the classical domain, we have bits, in the quantum domain, we have qubits. In the classical domain, we do not have superposition. In the quantum domain, we have superposition. In the classical domain, the states are simple, binary. In the quantum domain, the states can be complicated depending on the physical properties of the particle. So we need some sort of physically encode the data. Okay. So most prominent methods of data encoding that are available when we switch from classical to quantum is basis encoding, amplitude encoding, angle encoding, quantum associative memory encoding, and quantum random access memory encoding. So let's say the basis encoding, where a bit can be encoded into just the basis vector. So 0 goes to bracket 0, which can represent the horizontal polarization, for example, and 1 represents a bracket 1, which is the state of vertical polarization, let's say. Doesn't matter. So the n-bit string x equal to x1 to xn can be encoded in the state of n qubits as x1 to xn, right? Which is a basis state. So an example, classical data is 101 and quantum state is bracket 101. And we know that the space requirement is order n, the time requirement is order n for this kind of data. The next type of encoding that we need in quantum machine learning is called amplitude encoding. So we have a vector with unit norm. We can represent it as a quantum state with respect to a fixed basis vector phi I. So phi I are the basis vector. For example, phi 1 can be the horizontal polarization, phi 2 can be the vertical polarization, and the dimension can be 2. Only 2 types of polarization. So small d can be 2. So depending on the dimension, we can have the basis states phi 1, phi 2, phi d, and we can represent our arbitrary state psi as a weighted combination of the basis states. That is precisely the superposition. So this is amplitude encoding. So example, classical data 0.6, 0.8, quantum state 0.60 plus 0.81. Of course, it is not normalized. So the next level is to normalize. So if D is the dimension, the space and the timing requirement is logarithmic mostly. Application quantum k nearest neighbor has this kind of application. Then we have angle embedding is performed by applying rotation using the quantum gate along the values to encode. So for example, if we have the classical data 0.5, 1.2, we can have the quantum state as, let's say, Ry 0.50, tensor Ry 1.20. So this Ry 0.5 and Ry 1.2 denotes rotation. We know that this bracket 0 is nothing but a vector, a column vector. So this Ry is a matrix which multiplied with the column vector gives you another column vector. So that is the transform vector. So Ry theta is nothing but cos theta by 2 minus sin theta by 2, sin theta by 2, cos theta by 2. So that's the rotation by an angle theta by 2, anti-clockwise. So quantum associative memory mapping. So it uses superposition to store a group of data. So for example, if x0, x1, xm minus 1 becomes my data, where each xi is an n bit number, then we can represent x by this particular state, where 1 by root m is the superposition of the encoded values. Okay. Then QRAM encoding is a mechanism that allows accessing classically stored information in superposition by querying an index register. So what is my original data? Looks like this: x0, x1, xm minus 1. So it's an m size data. Each xi is an n bit number in the classical data. In the quantum domain, we can convert the bit into qubit, and then we have indices I. So this basically creates an association between the level I and the data xi. Because RAM is random access. So whenever we can go to the ith index vector, we can find the associated data vector. That is the idea. That's why it's called QRAM encoding. Okay. So application is quantum database search, quantum cryptography. Fine. Now, in order to perform quantum machine learning task, we need to have certain quantum tools. So for example, QDIST, quantum Fourier transform phase estimation, quantum technique for eigenvalue, eigenvector computation, HHL algorithm, minimum searching algorithm, etc. So we'll discuss only some of them as model examples. Okay. So QDIST is a method for computing distances between vector points. Suppose A and B are two vectors of dimension 2 to the power n, because that's the dimension of a Hilbert space for n qubits. Then the amplitude encoding of A and B in n qubit is given by normalized vector. That's why 1 by mod of A is given there. That's basically the length of A. Then AII. So now we define psi and phi as a combination of these A and B vector. Finally, we have this circuit where on the left of the circuit, we feed Q1, Q2, Q3, Q4 as Q1 as 0, Q2 as phi. Phi is already given here, defined here, A0 minus B1. And psi is 0 tensor A plus 1 tensor B. So psi is Q3, Q4. That's a 2-qubit state. That's psi. So at the input side, we'll give these values to the left-hand side of the circuit. And then we can show by using the properties of Hadamard gate and the measurement that is happening here, okay, that finally we are going to measure the distance between the circuit. Long story short, if we do the calculations, we can show that mod of A minus B whole square, which is basically the distance between the two vectors, can be written as twice times C. C was given as mod of A square plus B square, 2 times C, then times 2 times probability of 0 minus 1. Why this probability of 0 is coming? Because when you perform measurement in this quantum circuit, as output, you are going to get either 0 or 1, because it's a 1-qubit state on which you are performing the measurement. You are not performing the measurement on all the 4 qubits. You are measuring the state only on Q1. So that will give you either 0 or 1, one of the basis states. So the probability of 0, if you perform this experiment multiple times, the probability of 0, you calculate the proportion from the proportion of 0. And then you plug in here, you get A minus B whole square mod. Basically, the distance between two vectors are calculated. Okay. So complexity of calculating Euclidean distance between two vectors in r to the power d in the quantum subroutine QDist is order of log d. Remember, in the classical domain, if we want to find distance between two vectors, it has to be order d, because every component wise we have to calculate the distance. But because of superposition, we have the advantage here. It is not order d, but order log d. Application: quantum k-means clustering, quantum k-nearest neighbors. Because any algorithm on clustering or nearest neighbor decoding, ultimately it is based on distance. So in k-means cluster, what do? We have the cluster centers, and in the next iteration, every data point we assign to a particular cluster center, as if this data point belongs to this particular cluster. How? We calculate the distance between a particular data point and every cluster center, and we find out which is the shortest distance. This data point is nearest to which cluster. So in the next iteration, we are going to assign to that particular cluster, right? So in order to decide this membership of every element in a cluster, we need to find out distance between 2 points. So distance between 2 points becomes a subroutine in our task. That subroutine in the classical way of solving gives order d time, where d is the dimension, but quantum way of solving gives order log d time. So we have a speed up. So here, quantum k-means clustering, quantum k-nearest neighbor problem definitely gives a speed up from d to log d with respect to classical algorithms. Okay. Similarly, we have quantum Fourier transform, which is defined as if we have an n-bit binary representation of the decimal x by the vector x1, x2, xn, and we denote bracket x to be the bracket x1, x2, xn, then the quantum Fourier transform of such an input vector is given by the right-hand side expression. So where capital N is nothing but 2 to the n, the dimension of the Hilbert space, and we have e to the power 2 pi I jx summation over j. Here I is the complex number I, and j is the index, j equal to 0 to n minus 1. And similarly, we have inverse Fourier transform. Now, long story short, We can have the circuit for quantum Fourier transform, where we have Hadamard gates as well as this phase gate Tk, where the phase gate Tk is denoted by 100 e to the power 2 pi I divided by 2k. So this quantum Fourier transform, the complexity is order n square, and it is applied in Grover search algorithm, in HHL algorithm, in quantum phase estimation algorithm. So there are so many applications of quantum Fourier transform. So let's discuss one of them, say quantum phase estimation. How this Fourier transform is used. So what is the quantum phase estimation problem? The problem is as follows. If U is a 2 to the n cross 2 to the n dimension unitary operator, and if phi is an eigenvector of U, then U phi is equal to e to the power I gamma phi, where gamma is any real number, right? In other words, you see, because U phi is e to the power I gamma phi, where e to the power I gamma is nothing but a scalar and U is a matrix. So that means e to the power I gamma is an eigenvalue of U. That is the definition of eigenvalue, right? Ax equal to lambda x. Instead of lambda, instead of A, we have U. Instead of lambda, we have e to the power I gamma. So now our goal is to find out a good approximation of gamma with high probability. Okay. So that means if we find out the eigenvector, because or eigenvalue, e to the power I gamma is an eigenvalue. If we find out the eigenvalue, we can find out gamma with high probability. So we replaced gamma by 2 pi theta and becomes U phi becomes e to the power 2 pi I theta phi. So in quantum phase estimation, we estimate theta from which we can determine gamma. And this is the circuit where we have lot of zeros on the left of the circuit because we want to initialize, and phi is the input state where this theta is hidden within phi, because this gamma is depending on phi and 2 pi theta is depending on gamma. So therefore, eventually gamma depends on the state phi. Okay. So after the inverse Fourier transform, after we measure, we see that x will be 2 to the power n theta with high probability. Okay. So therefore, because if x becomes 2 to the power n theta, then it becomes e to the power 0, which becomes 1. Okay. So theta can be measured as x by 2 to the power n, where x is the value that we are measuring by this measurement device. So here the complexity is order n square. Application is quantum principal component analysis and quantum graph spectral cluster. Okay. So, I have shown you that the finding eigenvalue. So quantum Fourier transform is a method of finding eigenvalue, and the finding eigenvalue can be used in quantum phase estimation. And why quantum phase estimation is important? Because quantum phase estimation can be used in quantum principal component analysis and quantum graph spectral clustering. Okay. So remaining of the talk, we'll have interactive question answer session. Let's say 10 minutes we have left. So any questions, please feel free to ask. We can discuss, or any comments that you can have. Okay.
Thank you so much, sir. So, audience, do you have any question to ask?
Hello, sir.
Hello.
I want to ask a question with respect to principal component analysis technique. So in classical machine algorithms, if we apply principal component analysis, so it affects our some it affects with respect to some data loss. So if we want to apply the same PCA with respect to quantum ML techniques, can we reduce the data loss, or it may happen something else with respect to our data, because the
No,
data
so
is
yeah,
the
so see, so basically what is happening, if you try to see that any classical machine learning task is decomposed into multiple subtasks, right? So in the classical principal component analysis, what we do, we basically find eigenvectors, and then eigenvectors with highest associated with highest eigenvalue, we rank them and find out the principal component, right? Now, so that means finding eigenvector of a matrix or a data matrix is very important problem. It's a sub problem. It's a subtask under principal component analysis. There can be many other steps, but this is the main sub-step. Now, what do we mean by quantum PCA? Means those steps that happening before the eigenvalue finding and after the eigenvalue finding, there are a lot of things that are happening in principal component analysis. We're not changing those steps, but as if the subroutine of finding the eigenvalue, we are outsourcing it to quantum device. And to outsource it, what we have to do? We have to encode the classical data into quantum data. We have to apply quantum method of finding eigenvalue, which is the quantum phase estimation and quantum Fourier transform, which we just saw. And then as output, we'll get some data, which again we have to convert back into classical encoding, right? So if the data is not clean, if the data is not homogeneous, if the data has some implicit problem, right, which may lead to data loss or data inconsistency, that may happen in quantum domain also, because it is a property of the data, right?
so means the data loss maybe is inevitable in both classical ML
Yeah,
and
inevitable
quantum
in
ML.
both, but one can study the relative data loss, that whether it is happening.
Any question? Any more question from audience side?
Because hello sir.
Yeah.
Yes, you.
So in continuation to that, why ask that? In previous session also I asked about training LLM model with respect to billions of parameters. So to be basic, if I want to predict the next token or next word, I have to feed all the billions of parameters to train the model, right?
Yeah.
So with respect to this technique, if I want to predict the next token and I want to also reduce my parameters for less consumption of say energy, hardware, or say other multiple features. So with respect to that, if I am doing so, how my uh, classical system will behave, and how will my quantum system will behave, because at the end we want to be efficient in all parameters, say cost, or say hardware, or say implementing algorithm, or
Okay,
building
okay. No, no,
algorithm.
I got your point. Okay. So right now, the quantum machine learning with respect to classical machine learning, what advantage it is giving is in terms of time. You saw that some task that in the classical machine learning we need order d time, it can be done in order log d time. Or maybe some tasks which can be done in, let's say, d to the power some exponent, which can be done in linear time, let's say in quantum domain. So that speed advantage is there in the quantum for some tasks. And if those tasks happen to be used in any machine learning algorithm, then we say, okay, we can apply now quantum machine learning. So quantum machine learning is not a general technique that if you give any classical machine learning problem, we have an equivalent quantum machine learning. No, it actually may not give you time reduction. It may increase the time also, because you have to this classical to quantum encoding, then quantum measurement, then quantum to classical encoding. It may take a lot of time. Only if the particular quantum algorithm has this feature of better running time than classical. Not all quantum algorithms are of that sort, but only if your machine learning task can be modeled in such a way that it involves one of those algorithms which happen to have better quantum version than classical, then we can plug in that component into the classical machine learning scenario and call it quantum machine learning. Actually, it's not quantum machine learning. It's actually offloading or outsourcing a component of classical machine learning, a black box of a huge classical machine learning operation into quantum. So that is the current scenario. And mostly the advantage is not in terms of efficiency, but in terms of time. Right.
And cost.
Since it is happening in less time, so efficiency is coming indirectly. How? Since it is happening in less time, so we can train more data if we have the same amount of time. In quantum, suppose we have 1 hour in the classical machine, 1 hour in the quantum machine. Because given a fixed size data set, quantum will take less time. Therefore, if we fix the time, the number of data point on which the classical can train in 1 hour increases in quantum, right? If we fix the time. So that increases the efficiency indirectly.
Okay.
So right now, quantum machine learning is standing at this stage.
Okay. So I just want to ask another question, but it is not with respect to particular session. Uh, in other sessions, irrespective of this FDP, I also attend another sessions with respect to quantum ML. So I particularly gain insights with respect to QML algorithms. But I want to ask, sir, if I want to build an entirely unique algorithm which is indisciplinary within the discipline, say mechanical engineering and machine learning, or say civil engineering and machine learning with respect to quantum input.
Okay. So here is okay. I know what you are asking. So here is the situation. So you see, quantum machine learning is not the proper terminology. It's a buzzword. It's an overhyped word that people are using to, especially in the industry, it is happening. The small fishes are trying to encash the big fishes. But actually it is what? We have the classical machine learning. It has a lot of black boxes connected together. One black box is outsourced to quantum, because that black box has a mathematical task which can be done faster in quantum. Maybe all the boxes cannot. So similarly, in your civil engineering domain or in your mechanical engineering domain, whatever problem you have, in your civil or mechanical engineering domain, if you have a problem, that problem involves a particular operation which can be done in quantum faster, you can plug quantum only in that part. And you can call it whatever. You can call it quantum only that part, or you can call it quantum civil, quantum mechanical. It does not make any sense. But the point is, particular tasks can be performed faster in quantum than classical, not arbitrary tasks. So when quantum computing came in 1980s, people had the dream that quantum means faster. Anything, if we change from classical to quantum, it is super fast. But that is not true. Okay.
So quantum system has its own disadvantages and advantages also.
Yes, of course. The disadvantage is the bottleneck, the maintenance of the state, the cost of maintaining the physical states of these electromagnetic devices or superconducting devices or nuclear magnetic resonance devices. So that involves a lot of cost, and also some classical operations, if we convert to quantum, it is going to take a lot of time, more time than classical itself. So it's not a panacea. So in my view, quantum machine learning is not quantum. Quantum machine learning is always hybrid as of now. It's 90%
Okay,
classical.
sir. Thank you. Thank you.
90% classical and 10% quantum. Okay.
Okay. Because in that session, I heard that all of the newbies in quantum field, they are just taking up the generic classical algorithms and just trying to implement some
There are a
quantum
lot
code.
of papers. Let me tell you, there are a lot of papers coming every day in different journals, conferences, written by faculty and students alike. They are translating any classical, component, classical machine learning. They are just, changing everything to quantum and calling it quantum machine learning. But which they are, running quantum simulators on small data, maybe a data of size 20, data set of size 20, data set of size 50, and showing, see, I have an advantage. That does not make any sense, because arbitrary classical problem, arbitrary classical algorithm cannot have necessarily an efficient quantum counterpart. Okay. That has to be validated for a proper research.
Okay, means classical analogy is still be
Anything
important
classical can
and
be
will
converted to quantum. Anything classical can be converted to quantum, but that will not necessarily give you an advantage. Okay, that is the point I'm trying to make.
So one more.
Thank you very much.
Yes.
Sir, one thing, sir. So for example, K-means clustering algorithm is there. How we can solve with respect to the quantum? Is it possible to explain?
Because K-means clustering involves computing distance in some step of that algorithm, and we know that given any two vectors, we can compute distance of those two vectors using quantum algorithm much faster than classical algorithm. So that tiny part of K-means is now replaced by a quantum module. And the whole thing we are calling quantum clustering, quantum K-means, it is not. Okay, it's a hybrid clustering.
Okay.
With the distant computing part outsourced to quantum device.
Okay, sir. So before going to the quantum machine learning, first we have to identify the problem. We have to understand that this problem cannot be solved using classical computer. Then we should go for
No, it can be solved.
computer.
It can be solved.
Right?
See, any problem can be solved in classical computer. Any problem can be solved in quantum computer. That's not a problem. You can multiply 3 times 5 in classical ALU circuit. You can multiply 3 times 5 in quantum circuit. But multiplying 3 times 5 in quantum will take a lot of time, lot more time.
Time as well as it will not be cost effective also.
Yes, exactly.
Right.
Okay,
right.
though quantum factoring is polynomial, but that
Yeah.
polynomial effect comes as an asymptotic time complexity, as a long run when n is large. So if we could compute, let's say, factoring of a 10,000 digit number, then we could have quantum advantage. But that is not a reality, because managing 10,000 qubits is impossible with the current technology. Okay, so that is the point. That's the technological limitations that we are having now.
No, but nowadays people are just like Rishikesh told, yes, people are doing like this and papers are getting published. So for
Yes,
research
but
work,
they
if
do
we
not
want,
make any sense.
okay,
Most of them
that
do not make any sense.
any sense. Okay, okay. So the people who are showing the results, basically they are just doing the simulation. They are not
Yes.
implementing or testing on the quantum hardware.
Yeah,
Right, sir?
So we are
Okay.
not expecting that everybody will have access or will test on quantum hardware. Even if they are doing simulation, it should be meaningful. They should identify some subtask within the classical task which has quantum advantage, right?
Okay, okay. Thank you, sir. Thank you
Yes.
so much, sir, for very insightful session, sir. Thank you. Thank you so much.
Welcome. Welcome.
Thank you so much, sir. With this, we are closing session 8. We'll meet tomorrow.
Hello, sir. Here I would like to request that please share the PPT.
Okay, yeah, I'll share with the organizer and they can share
Yeah.
with you.
Yeah, sir. Yes, sir. Thank you so much, sir. Thank
Okay.
you.
Welcome. Okay, so
Thank
may
you,
I
sir.
leave?
Yes, yes. Okay. Good night, sir.
Yes, good night.
So with this, we are ending this session. Thank you, participants. We will have our next session on tomorrow from 6 p.m. Thank you.